You're about to uncover one of the most surprising truths in modern science. This video breaks down everything you came here to understand, clearly and completely. From the basics to the mind-blowing discoveries, you've clicked exactly the right video. Matter doesn't just change form, it rewrites its own rules in ways that still baffle scientists today. Find out how many states of matter actually exist, what makes them appear or vanish, how light can behave like a substance, and how these discoveries are already shaping future technology. How many states of matter are there? Most people grow up learning that matter comes in just three forms: solid, liquid, and gas. But scientists have discovered that matter can exist in many more states, each one stranger and more fascinating than the last. The number of known states has grown as technology has advanced, especially in laboratories where extreme conditions can be created. Some states exist at temperatures close to absolute zero, where atoms barely move. Others form only in the hottest places in the universe, like just after the Big Bang. These new states of matter reveal hidden behaviors and open doors to ideas that change how we think about the universe. Understanding how many states of matter there are is not just a science question, it's a journey into the nature of reality. Atoms in a solid are locked in place, vibrating gently without changing position. This tight structure gives solids their rigid shape and fixed volume. From mountains to metal tools, the solid state gives form and stability to the world around us. As heat increases, solids change into liquids, where atoms are still close together but free to move around. This gives liquids the ability to flow, take the shape of containers, and adapt while still holding a consistent volume, like water in a glass or blood in veins. Gases behave completely differently. Their particles spread far apart and move freely, filling any space they're in. This lack of structure means gases don't have a definite shape or volume. Air, steam, and helium balloons are all examples of gases in everyday life. At even higher energy levels, matter becomes plasma. In plasma, atoms break apart into charged particles, electrons and ions. Plasma conducts electricity, responds to magnetic fields, and glows with energy. It's found in lightning, neon signs, and the blazing core of stars. These four states, solid, liquid, gas, and plasma, are considered classical because they are common and easy to observe. Matter can behave in magical ways when cooled close to absolute zero. In this extreme cold, certain atoms slow down so much that they stop acting like individuals and begin to behave as one giant quantum particle. This strange state is called a Bose-Einstein condensate, or BC. It was first predicted by Albert Einstein and Satyendra Nath Bose in the 1920s, but it wasn't created in a lab until 1995. In a BC, particles known as bosons all fall into the same energy state, merging into a single wave-like entity. In a Bose-Einstein condensate, quantum effects become visible on a macroscopic scale. Instead of bouncing around randomly, atoms move in perfect harmony. Light passing through a BC slows down dramatically, showing how this state can affect even electromagnetic waves. Scientists use magnetic and laser traps to cool and hold atoms still enough to observe this effect. BCs are not just a curiosity, they provide insights into quantum mechanics, superfluidity, and coherence. They have become a key tool in researching quantum computers and precision measurement systems. This state shows how cold can reveal the unity hidden beneath the chaos of particles. It proves that matter's behavior can shift entirely with the right conditions. Unlike BCs, which are made of bosons, fermionic condensates are formed from particles called fermions. Fermions follow different quantum rules. They resist occupying the same state. But when cooled to nearly absolute zero and paired up in special ways, they can form a condensate that behaves like a superfluid. This was achieved experimentally in the early 2000s, expanding our view of what matter can become. A fermionic condensate flows without resistance, like a perfect liquid. It's a phase where friction disappears and particles glide effortlessly past one another. This makes it especially valuable for studying superconductivity and the way particles behave in neutron stars. This state is incredibly delicate and requires extreme precision to create and observe. It reveals how particles that normally repel each other can be coaxed into a synchronized quantum state under the right conditions. Fermionic condensates demonstrate the richness of quantum behavior, especially when different types of particles interact. In the first microseconds after the Big Bang, the universe existed in a state of unimaginable heat and density. In this moment, matter was not made of atoms or even protons and neutrons. It was a sea of free quarks and gluons, particles that normally make up protons and neutrons but were completely unbound. This is called quark-gluon plasma, and it is one of the most extreme states of matter ever studied. Scientists recreate this state using powerful particle accelerators, such as the Large Hadron Collider. In tiny, high-energy collisions, they observe short-lived flashes of this ancient fiery state. What they find surprises them. The quark-gluon plasma flows like a nearly perfect fluid, with almost no resistance. This state offers a look back into the very origin of the universe. It helps scientists understand the forces that hold atoms together and the transition from free particles to structured matter. Studying quark-gluon plasma is like digging into time itself, unlocking secrets of the earliest moments after creation. Some liquids break the rules. When cooled below a certain temperature, helium-4 becomes a superfluid able to flow endlessly without friction. It can climb walls, leak through tiny cracks, and spin in a container forever without slowing down. This bizarre behavior reveals a quantum state where viscosity vanishes and flow becomes eternal. Superfluids are useful in physics research because they show how matter behaves in perfect coherence. They also play a role in understanding the interiors of neutron stars, where similar states might exist under immense pressure and gravity. Even in labs, superfluids are hard to control, but deeply fascinating. This state is not limited to helium. Other materials can become superfluid under the right conditions, especially in ultra-cold settings. The discovery of superfluidity opened a new world of quantum effects that behave at large scales. It turns the everyday concept of liquids on its head and suggests that matter can move in ways that seem impossible. In nature, solidity and flow don't usually mix, but in the case of a supersolid, matter seems to break this rule. It is a state that behaves like a solid with a crystal structure while also having the ability to flow like a superfluid. This combination was once thought to be impossible, but experiments with ultra-cold helium and other systems have shown signs of this behavior. The particles in a supersolid are arranged in a repeating pattern, yet they can move through the structure without resistance. This strange duality means that the state can maintain both shape and perfect motion. Theoretical predictions existed for decades, but actual evidence came only recently in specialized lab setups. Supersolids provide a bridge between order and fluidity. They challenge our understanding of how particles interact and hint at new ways of creating materials with unusual mechanical and flow properties. As research continues, supersolids may unlock insights into symmetry-breaking, quantum coherence, and future technologies. In ultra-cold gases, atoms can behave in strange and delicate ways. A Rydberg polaron forms when a single atom is excited to a high-energy state called a Rydberg state, and its electron orbits become so large that dozens or even hundreds of other atoms can fit inside. These other atoms get trapped inside the orbit, forming a gentle cloud bound by the giant electron's presence. This state was first observed in Bose-Einstein condensates and is highly fragile. The Rydberg atom acts like a net, capturing nearby particles with its oversized electric field. This behavior is not found in everyday matter and shows how quantum effects can stretch and combine atomic structures in unusual ways. Rydberg polarons open up new paths for studying weak interactions and long-range forces. They reveal how energy levels and fields can be manipulated to create strange forms of matter that are soft, cloud-like, and highly sensitive. These discoveries may lead to applications in quantum sensing and precision measurement. Ordinary crystals repeat in space. Their atoms are arranged in patterns that stay the same from place to place. But time crystals do something no one thought possible. They repeat in time. Without using energy, their structure shifts in a regular rhythmic cycle, forming a kind of perpetual motion at the quantum level. This doesn't break the laws of physics, because the motion is not used for work. It simply happens as part of the system's lowest energy state. Time crystals were first created in 2016 using carefully controlled quantum systems. Researchers used ions trapped by magnetic fields and lasers to force a kind of predictable ticking where the system flips back and forth endlessly. This happens even when no outside force is applied, making time crystals unlike any other state of matter. This state has potential use in quantum computing, where predictable cycles can help protect information. More importantly, Time crystals reveal that matter can organize not just in space, but in time as well. They challenge old ideas of stability and show how quantum systems can behave in new, rhythmic ways that repeat not just in structure, but in motion through time. Light normally passes through space without interacting with other light. But under the right conditions, scientists have found ways to make light particles, photons, behave as if they have mass and even stick together. This unusual behavior creates photonic matter, where light acts more like a solid or fluid. It's a strange form of matter that doesn't involve atoms at all. To create photonic matter, researchers use ultra-cold gases or special optical setups where photons can be slowed down and made to interact. In this state, light can bounce off itself or form structures that mimic the behavior of physical objects. It's like making bricks from pure energy. Photonic matter could be useful in building optical circuits, quantum computers, or devices that use light instead of electricity. It also helps scientists explore new laws of interaction, where the boundary between energy and matter becomes blurred. This state shows that even something as intangible as light can be shaped into something that behaves like substance. Some physicists believe the very particles that make up matter, like electrons and photons, might not be fundamental. Instead, they could emerge from something deeper, like a web of interactions at the smallest scales. One idea is the string-net liquid, a hypothetical state of matter where particles and forces arise from the waving and twisting of invisible strings. In this state, the universe behaves like a fabric woven from quantum threads. String-net liquids are not observed in nature yet, but they are predicted by theories in condensed matter physics and quantum field theory. In this view, particles are not the starting point, they are ripples in the underlying net. This concept might explain why light exists and how it behaves the way it does. If string-net liquids are real, they would be more than just a new state of matter. They would be a clue to the hidden structure of the universe. They suggest that everything we see might come from patterns of entanglement, not from hard particles. It's a vision of matter as information and relationships woven into space itself. Inside a white dwarf star, matter is crushed by gravity so strongly that atoms break apart. Electrons are squeezed so tightly that they form a special type of pressure, resisting further collapse. This creates electron-degenerate matter, a state where particles are held up not by thermal energy but by quantum rules. It's extremely dense. Just a spoonful would weigh tons. This state happens when gravity overwhelms ordinary atomic forces and electrons create a kind of quantum support structure. It's governed by the Pauli exclusion principle, which says that no two electrons can occupy the same state. This creates an invisible pressure that holds up the star. Electron-degenerate matter shows how quantum physics can shape the structure of stars. It helps explain why white dwarfs don't collapse further unless they exceed a certain mass. It also shows that matter has hidden strength deep inside, waiting to reveal itself under enormous pressure. Even more extreme than electron-degenerate matter is neutron-degenerate matter found inside neutron stars. When a massive star explodes in a supernova, its core collapses into a ball so dense that protons and electrons fuse into neutrons. These neutrons pack together tightly, forming one of the densest states of matter in the universe. Neutron-degenerate matter is supported by a similar quantum pressure, this time coming from the neutrons themselves. The result is a star just a few kilometers wide, but with a mass greater than the Sun. Its gravity is so strong that it bends light and warps time. This state is important because it reveals the limits of matter's resistance to collapse. It may also lead to new discoveries about superfluidity, superconductivity, and the behavior of quarks under extreme conditions. Neutron stars are cosmic laboratories where this state is on display, showing what happens when matter is pushed to its absolute limits. At incredibly high energies, the inside of a proton becomes a wild storm of gluons, the particles that hold quarks together. When protons travel near light speed, these gluons multiply and pile up in strange ways. They slow down and form a new state called color glass condensate. It's not made of color in the usual sense, but from color charge, a property in quantum physics related to the strong nuclear force. This state of matter behaves like a glass because it's disordered but rigid, and it's called a condensate because many particles crowd into the same state. It's been studied in particle accelerators, where fast-moving nuclei collide and reveal hints of this new form. Though short-lived, it helps scientists understand the behavior of matter under extreme pressure and motion. Color glass condensate gives clues about how the early universe looked just before quark-gluon plasma formed. It also helps researchers explore the strange relationship between speed, energy, and particle interactions. This state shows how the faster matter moves, the stranger it becomes. It's a doorway to understanding high-energy collisions and the nature of strong nuclear forces that bind the core of all matter. The state of matter depends on the environment around it. Temperature, pressure, and energy levels change how particles behave. Cold temperatures can freeze matter into solid or quantum states, while extreme heat turns it into plasma or quark soup. High pressure creates dense forms found in stars. Magnetic and electric fields can also alter particle behavior. These conditions allow scientists to control how matter transforms. In laboratories, exact conditions help reveal new states that never occur naturally on Earth. This aspect is important because it explains that matter's behavior is not fixed. It responds to its surroundings in remarkable and varied ways. Matter changes from one state to another through a phase transition. Melting, boiling, and freezing are common examples, but many complex transitions exist in exotic states. A superfluid may become a normal fluid with a small temperature change. These transitions depend on particle motion and energy exchange. Phase changes also help scientists study energy, structure, and atomic behavior. Some phase transitions happen suddenly while others occur gradually. Understanding these shifts helps explain why materials act differently under certain conditions. Phase transitions are more than physical changes. They show how deeply connected energy, movement, and structure are in the behavior of matter. Some states of matter only appear in extreme environments. Inside stars, black holes, or during particle collisions, pressure and temperature reach unimaginable levels. These places give rise to plasma, neutron-degenerate matter, and other rare forms. Scientists recreate these conditions in high-energy labs to study them in controlled settings. These extreme environments push particles into new arrangements and reveal forces not seen in normal conditions. Understanding matter in such settings helps explain cosmic events and the origins of the universe. This shows that nature behaves very differently when pushed to the limits, making extreme environments valuable windows into the unknown. Quantum mechanics governs the behavior of particles at atomic and subatomic scales. In quantum states of matter, particles can occupy the same space, flow without resistance, or become entangled. These behaviors defy classical expectations. States like Bose, Einstein, condensates, and time crystals arise only because of quantum rules. Quantum mechanics reveals how matter can exist in unified or wave-like forms. It also helps explain why certain states are stable while others are chaotic. This highlights how quantum theory is essential for understanding the strange and often invisible behaviors of matter. Without it, many modern states of matter would remain unexplained. In space, matter behaves in ways never seen on Earth. In white dwarfs, electrons are packed tightly, forming electron-degenerate matter. In neutron stars, neutrons are squeezed together, creating ultra-dense states. These astrophysical states show how gravity and pressure can completely reshape matter. They're crucial for understanding how stars evolve, die, or collapse. Telescopes and space missions help us study these distant states. Even though they can't be recreated easily on Earth, they guide theories and predictions. This aspect shows that outer space is full of extreme laboratories where matter forms in powerful, mysterious, and fascinating ways we are just beginning to understand. Energy controls how particles move, vibrate, or combine. The more energy particles have, the more chaotic their movement becomes. This causes transitions from solids to liquids, gases, and plasma. The type of particle, boson or fermion, also matters. Bosons can share states and form condensates. Fermions behave differently, resisting crowding. These fundamental properties shape which states of matter can form. Whether it's temperature, speed, or charge, energy and particle type determine matter's structure. This helps explain why matter doesn't behave the same everywhere. The identity and energy level of particles unlock different behaviors and make new states of matter possible. Exotic states of matter are not just curiosities, they have real applications. Superfluids may lead to frictionless systems. Time crystals could store stable quantum data. Superconductors already transport electricity without loss. Scientists use these states to test new technologies and explore quantum computing. The strange behaviors of exotic matter offer tools for faster computers, precise sensors, and new materials. Though many are still experimental, their potential is enormous. This aspect shows how understanding unusual forms of matter can lead to breakthroughs in daily life. What starts in a lab may soon become essential in medicine, space, energy, and communication. Scientific ideas must be tested to be accepted. States of matter are confirmed through careful experiments. Scientists use powerful lasers, cooling systems, and particle colliders to observe how matter behaves. Condensates, plasma, and quark-gluon states have all been measured and studied in labs. Observing particle motion, energy loss, or radiation patterns gives proof that theories are correct. Without this evidence, concepts stay theoretical. Experiments make the invisible visible and turn predictions into knowledge. This proves that real-world testing is essential. It connects equations with observations and helps us trust what we know about the many strange forms of matter. Many states of matter were predicted before they were seen. Scientists use mathematical models and simulations to describe how matter might behave under unknown conditions. Time crystals, superfluids, and other forms were ideas on paper long before they appeared in labs. These predictions guide experiments and inspire discovery. They help scientists understand what's possible, even if it hasn't been built or observed yet. This aspect shows that theory is more than guesswork. It helps uncover truths before we can measure them. Predictions about matter challenge researchers to look deeper and create conditions where new realities can be confirmed. Temperature has a powerful effect on how matter behaves. At extremely high temperatures, atoms break apart into plasma or quarks. At near absolute zero, particles stop moving and form condensates. These extremes reveal the full range of particle behavior. Scientists use advanced tools to reach these conditions, including cryogenic cooling and particle accelerators. Different temperatures allow different forms of order or chaos. This shows that matter's state is never fixed. It depends on energy levels. Pushing temperature to its limits opens new paths for research, allowing discoveries that cannot happen in normal conditions found on Earth's surface. Gravity compresses matter and reshapes its structure. When gravity is intense, like in neutron stars, matter changes completely. High density forces particles into compact forms that don't exist naturally on Earth. This aspect helps explain why some stars collapse instead of exploding. It also shows how matter can resist gravity using quantum pressure. The more gravity squeezes, the more unusual the response becomes. This leads to states like neutron degenerate matter. Understanding gravity and density helps scientists predict how stars die, what black holes hide, and how the universe holds itself together under pressure that ordinary matter can't handle. Light travels differently through certain materials. In some states of matter, it slows down, changes direction, or even behaves like it has mass. Inside Bose Einstein condensates, light moves much slower than usual. In photonic matter, light particles interact like solids. This unusual behavior lets scientists control light in new ways. Light's interaction with matter reveals hidden properties and helps design new technologies. From fiber optics to quantum communication, understanding how light moves through different states is essential. This shows that even something as fast and simple as light can be shaped by the hidden physics of exotic matter. Some exotic materials can store information in quantum patterns rather than physical memory chips. Time crystals and topological matter preserve data over time without needing constant energy. These properties are valuable in quantum computing, where stability is hard to achieve. In these materials, information is encoded in motion, spin, or entangled states. This makes them resistant to errors or loss. Understanding this storage method could lead to breakthroughs in technology. This aspect shows how matter can hold memory in new forms, expanding how we think about saving, transmitting, and protecting data. Exotic matter becomes a tool for the future of computing. New states of matter are still being discovered. Time crystals were confirmed only recently. Scientists are now exploring topological phases, strange superconductors, and other possibilities. Each new discovery adds to our understanding of how particles behave. These findings also raise new questions about what matter can do. As tools improve and theories deepen, more hidden states will likely appear. This highlights that science is never finished. Matter holds more secrets than we once thought. The journey of discovery continues, and with every new experiment we find more surprises about the invisible world that shapes the universe around us. Matter isn't just about particles, it's about how they arrange, connect, and move together. Some states of matter are defined not by what's in them, but by how their parts are ordered. Superfluids, crystals, and time crystals all show different ways particles can organize into patterns, flows, or cycles. This organization determines properties like conductivity, stability, and response to forces. Even slight changes in pattern can create huge changes in behavior. Scientists use this knowledge to design smart materials, sensors, and devices that respond in precise ways. Understanding how matter organizes itself helps explain everything from magnetism to the color of materials to the flow of electrons in a chip. It shows that the structure of matter is as important as its content. By mastering these patterns, we can shape the world at the smallest levels. States of matter we haven't discovered yet may already exist in deep space or microlabs. The more we look, the more we find that nature holds surprises in how particles behave. Future discoveries could include materials with perfect memory, gravity-defying flow, or new ways of interacting with energy and light. Scientists are designing better experiments, building stronger tools, and developing deeper theories to explore these frontiers. As we understand more about particles, forces, and dimensions, we may uncover matter that operates beyond our current imagination. The future of matter research is not just about finding more types, it's about understanding the unity behind them. Each new state brings us closer to seeing how everything is connected. These breakthroughs could power new technologies, help us explore space, or even reveal the structure of reality itself. Topological matter behaves in unusual ways because of its surface structure, not its internal composition. These materials conduct electricity only on their surfaces or edges while remaining insulating inside. Their stability comes from mathematical properties known as topology, making them resistant to disturbances. This unique behavior allows them to carry information with great reliability, which is essential for quantum computing. Topological insulators and superconductors are actively studied in condensed matter physics. They show that the shape and arrangement of a material, not just its particles, can create new and robust states. These discoveries reveal hidden orders in seemingly simple materials. An exciton condensate forms when electrons and holes, oppositely charged partners, pair up and move together as one fluid unit. These excitons exist in special materials under very cold conditions. When cooled enough, large numbers of excitons can collapse into a single quantum state, similar to a Bose-Einstein condensate. This state of matter allows for frictionless flow of electrical charge and may lead to energy-efficient devices. It represents a new way in which matter can organize through electron-hole interactions. Although still under active research, exciton condensates could revolutionize electronics by providing low-energy pathways for current without typical resistance. Strange superconductors, also called unconventional superconductors, do not follow the classic rules of superconductivity. In these materials, electrical resistance drops to zero, but the mechanism behind it is not fully understood. They often involve unusual pairing between electrons or strange magnetic behaviors. Found in materials like high-temperature cuprates and iron-based compounds, strange superconductors work under conditions different from conventional superconductors. They challenge existing theories and may reveal new quantum principles. Their discovery could help design superconducting materials that work at higher temperatures, transforming power grids, medical imaging, and quantum computing. These states remain mysterious but extremely promising for future technologies. Beyond the commonly listed 22 states of matter, physicists have proposed a wide range of additional states that may exist under extreme controlled or unexplored conditions. There are more than 50 states of matter if we include all known, observed, theoretical, proposed, and speculative forms discovered or predicted across physics, astrophysics, and quantum research. These lesser-known and often theoretical states emerge from studies in quantum field theory, cosmology, and high-energy experiments. Some are extensions of known phases, while others belong to entirely new frameworks. For example, preon matter is a hypothetical state made of particles smaller than quarks, proposed to exist in the early universe or inside black holes. Axion condensates involving dark matter candidates known as axions might form large-scale coherent structures in space and influence galaxy formation. In quantum systems, theorists explore non-Hermitian matter, where energy is not conserved due to particle gain or loss. These systems reveal strange behavior not seen in standard equilibrium physics. Many-body localized phases are another proposed class where disorder in a quantum system prevents particles from spreading, locking them into localized patterns. These phases defy traditional thermodynamics and are actively studied in disordered materials. In condensed matter, scientists investigate spin ices and spin liquids, exotic magnetic states where atomic spins fail to align even at absolute zero, resulting in frustration and emergent behavior. Fractal matter is a newer proposal where particles can only move in specific directions or dimensions, limiting their behavior in ways unseen in typical matter. Also proposed are non-abelian anyones, particles that do not obey standard boson or fermion rules and could form new quantum phases relevant to topological quantum computing. From astrophysics, strange quark matter, a possible ultra-dense form made entirely of up, down, and strange quarks, may exist in neutron star cores. Mirror matter is another candidate, a type of invisible matter that mirrors normal particles but interacts only through gravity. Together, these speculative and emerging states reflect the scientific belief that matter is far more diverse than what we observe daily. As research tools improve and theories evolve, the full list of matter's states could exceed 50 or even more, reshaping our understanding of the universe. The number of states of matter is far greater than what we learn in school. From the familiar world of solids, liquids, gases, and plasma, to the extreme and exotic like superfluids, quark-gluon plasma, and time crystals, each state reveals a different face of nature. These states aren't just categories, they are expressions of how matter behaves under different conditions, and they challenge the way we think about particles, forces, and energy. Studying these states opens doors to new technology, deeper scientific theories, and a greater understanding of the universe. They help us see that matter is not fixed or simple. It is flexible, surprising, and rich with behavior we are only starting to grasp. Each discovery is a step toward mastering the deep rules of reality. From the coldest temperatures to the hottest cosmic collisions, matter continues to amaze. And as scientists continue exploring, there is no doubt that even more astonishing states are waiting to be revealed. The journey into the heart of matter is far from over, and the possibilities ahead are as vast as the universe itself. Disclaimer: as an Amazon and other affiliate, I earn from qualifying purchases at no additional cost to you. Do you like the video and want to make videos like this? Turn text into stunning videos in seconds. Get free trial and unlock your creative potential. You can create even better videos than mine. No editor is required. Check out the link in the video description below. What's the most surprising way you think states of matter could affect your daily life? Let us know your thoughts or questions in the comments. And if there's a topic you want us to explore next, let us know. Your idea could shape our next video. Thank you for joining us on this journey through states of matter. Please like and share the video, and please do not forget to subscribe for more videos.